Hello friends, welcome to CEC Live Lectures. Dear friends, as you know that through our previous sessions we have tried to discover more and more on carboxylic acids, and we have discussed a lot in our two sessions on the same topic. Friends, today also we are going to talk on carboxylic acids only, and I would say that this is the third lecture where we are going to talk on nucleophilic acyl substitution reactions, and for the discussion on the topic we have with us in our studios Dr. Aparajita Chauhan. Dr. Aparajita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Dr. Aparajita Chauhan is an author of numerous books, and her books are admired by the students community as a whole. Friends, we know that you might have lots and lots of questions in mind while listening to the session too. So if you wish to ask questions, do note our toll-free number. Our number is 1800-110-430. I repeat, our number is 1800-110-430. You are requested to call in the last 10 minutes of the lecture only if you have questions related to the topic only. Now, I would like to welcome our guest, Dr. Aparajita Chauhan, once again. Hello, ma'am.
Hello, Deepika. Today we shall be talking on acidity, but before we proceed further, in our previous lectures, I had discussed the acidity of alkanoic acids, and what we found was that alkanoic acids are more acidic than alcohols and phenols, whereas they are less acidic than mineral acids. We also discussed the effect of substituents on the acidity of alkanoic acids, and what we found was that electron donating groups decrease the acidity of alkanoic acids, whereas electron withdrawing groups increase the acidity of alkanoic acids. In today's lecture, we shall be discussing the relative acidity of alkanoic acid and benzoic acid, and then we shall be discussing the effect of substituents on the acidity of benzoic acid. We shall also be discussing the acidity of isomeric benzoic acids, that is of ortho, para and meta substituted benzoic acids. So if we talk of the acidity of alkanoic acids and benzoic acids, what we find is that benzoic acid is less acidic than formic acid, but it is more acidic than rest of unsubstituted alkanoic acids. So what we find here is that when we talk of the relative strength of aliphatic acids and aromatic acids, we find that benzoic acid is a stronger acid than other alkanoic acids due to the presence of phenyl ring. The carboxylic group attached to an sp2 hybridized carbon ionizes to a greater extent than when it is attached to an sp3 hybridized carbon of the alkyl chain. Not only this, what we find is that the phenyl group stabilizes the carboxylate ion more effectively as compared to the alkyl group, because phenyl group exerts a minus I effect, thereby making the conjugate base a stable base or less basic in nature. Since the benzoate ion is more stable, it is more acidic than acetic acid. So now if we look into the pKa values of benzoic acid and acetic acid, what we find is that the pKa value of benzoic acid is 4.2, whereas that of acetic acid is 4.8. So what we find is that benzoic acid is more acidic than acetic acid, and benzoic acid will be more acidic than rest of the alkanoic acids also, like it will be more acidic than propanoic acid, butanoic acid, isobutyric acid, pentanoic acid. Now if we look into the effect of the substituents on the acidity of benzoic acid, then what we find is that if an electron withdrawing group is present on the benzene ring, that is, this electron withdrawing group can be a nitro group, a cyano group, a carboxylic group or a chloride. So what we find is that these groups will increase the acidity of benzoic acid, because they will exert minus I effect, or they may even exert minus I as well as minus R effect, due to which the negative charge will be delocalized and they will make the acid more acidic than benzoic acid. Whereas if an electron donating group such as methyl, methoxy or an hydroxyl group is present on the benzene ring, it destabilizes the benzoate ion and hence that particular acid will become less acidic than benzoic acid. So for this I have taken an example to illustrate this. That is, if we compare the acidity of tolic acid with tolic acid, benzoic acid, para-chlorobenzoic acid and para-nitrobenzoic acid, what we find is that para-nitrobenzoic acid is most acidic in nature. Reason being, when we look into the structure of nitro group, what we find is that nitro group, when present at the para position, will exert a minus I and a minus R effect, due to which the negative charge on the carboxylate group will be delocalized further, and this is a stable base. Hence, the acid will be acidic. This will be followed by para-chlorobenzoic acid, because the para-chlorobenzoate ion is stabilized by minus I effect of the chloro group. Whereas if we look into tolic acid, then what we find is that methyl group exerts a plus I effect, and due to this plus I effect, the negative charge is more on the carboxylate group, as a result of which the base is strong or it is unstable, and hence the acid is weak. So what we find is that if we look into the acidic strength of these acids, para-nitrobenzoic acid is most acidic, followed by para-chlorobenzoic acid, then benzoic acid, and para-tolic acid is least acidic in nature. Now I would like to discuss the comparative acidic strength of isomeric substituted benzoic acids. Now what we know is that acidic strength depends on two factors. First is the inductive effect, and inductive effect depends on the position of the substituent. That is, whether it is at the ortho position, para position or meta position to the carboxylic group. And second, it depends on the resonance effect. And this resonance effect is observed maximum at the ortho and the para positions. And what we know is whether it is an electron withdrawing or an electron donating group, these effects are strongest for substituents when they are present at the ortho and the para position. And another very important fact is that regardless of the fact whether the substituent has a plus I effect or a minus I effect, all ortho substituted benzoic acids are stronger than corresponding para and meta isomers, and this is called as an ortho effect. What I mean here is that if a group, whether it is electron donating or an electron withdrawing, when it is present at the ortho position, that particular acid will be more acidic than benzoic acid. Not only that, it will be most acidic among the isomeric acids. That means whenever we are discussing the acidity of ortho, para and the meta isomers, ortho will be most acidic. Let us look this into another. I have tabulated these results in a form of a table, and what we find in this case is that nitrobenzoic acid in this case will be most acidic, and if the substituent is at the ortho position, then it is most acidic, followed by a para substituted group, nitro group, and then the meta. Whereas when we look into the methyl group, that is if the substitution is a methyl group, then if the substitution is at ortho position, then what we find is that this orthotoluic acid is going to be more acidic than normal benzoic acid, that is unsubstituted benzoic acid. Whereas if the substituent is present at the meta or the para positions, then those acids are going to be less acidic than benzoic acid, as well as they are going to be less acidic than orthotoluic acid, as well as orthotoluic acid will be most acidic among the isomeric compounds, followed by meta and the para. Now let us look into the overall acidic strength of the isomeric nitrobenzoic acids. Then what do we find is that the orthonitrobenzoic acid is most acidic, followed by followed by para-nitrobenzoic acid, and then least is meta-nitrobenzoic acid. The reason being that when the nitro group is present at the ortho position or at the para position, it exerts minus I and minus R effect. And due to this minus R effect, the negative charge is delocalized further, thereby stabilizing the conjugate base. Hence, orthonitrobenzoic acid is most acidic, followed by para-nitrobenzoic acid. Meta-nitrobenzoic acid is least acidic because when nitro group is present at the meta position to carboxylic group, it is not able to exert minus R effect. Here only minus I effect is operative. Hence the order of acidity: orthonitrobenzoic acid, followed by para-nitrobenzoic acid, and least is meta-nitrobenzoic acid. So if we look into the resonating structures here, this is what I meant, that when the nitro group is present at the ortho or the para positions, it delocalizes the negative charge further, thereby stabilizing the conjugate base. Now if we look into the chlorobenzoic acids, then what we find is that chloro group exerts a plus R effect. Now you have to keep in mind that nitro group was exerting minus I and minus R effect, whereas in case of chlorobenzoic acids, chloro group is exhibiting a plus R effect, and at the same time it is also exerting a strong minus I effect. In this case, only minus I effect is the only factor which contributes towards the acidic strength, and we know that the inductive effect depends on the position of the substituent. So what we find is that inductive effect is maximum when it is present at the ortho position, followed by meta and then the para. So the order of acidity in case of chlorobenzoic acids is that orthochlorobenzoic acid is most acidic, followed by metachlorobenzoic acid, and parachlorobenzoic acid is least acidic. This can also be collaborated by the pKa values, that is the pKa value of orthochlorobenzoic acid is 2.9, that of metachlorobenzoic acid is 3.8, and pKa value of parachlorobenzoic acid is 3.9. So what we've seen here, what I've shown in this slide here is, that is if we have a methyl group. Now we know that is if I'm talking of a tolic acid, then tolic acid, this paratolic acid is going to be less acidic than benzoic acid, because methyl group will exert a plus I effect, as well as it will also exert a plus hyperconjugative effect, due to which the negative charge on the carboxylate group will increase. That is, it will destabilize the carboxylate group, thereby decreasing the acidity. That is, the base will conjugate base. Para-methyl toluate will be a stronger base, hence the acid will be weak. Similarly, if we take in case of halogens, then what we find is that in case of halogen, if I take an example of para-chlorobenzoic acid, then what we find is that when it is present, the substituent is present at the para position. It will stabilize the base because of the minus I effect. And hence, this will be more acidic than benzoic acid. Another very interesting example that I would like to discuss is that of hydroxybenzoic acids, and we know that an hydroxyl group will exert a minus I effect, which will be strongest at the ortho position, followed by meta and then the para. At the same time, it will exert plus R effect. So as I've discussed earlier, in this case again, the acidity will be decided by minus I effect. So what we find is that ortho hydroxybenzoic acid is most acidic, followed by meta hydroxybenzoic acid and then para hydroxybenzoic acid. Another important factor, what we find here is that when we are comparing the acidity of these acids, we find that ortho hydroxybenzoic acid is highly acidic. And what makes it so much acidic as compared to meta and para is that the carboxylate ion which is being formed here, the salicylate ion which is formed here, is stabilized by intramolecular hydrogen bonding. So what we find here is that because of this intramolecular hydrogen bonding, this is very stable. So the salicylate ion is stabilized by minus I effect of the OH group, as well as because of intramolecular hydrogen bonding. Hence we find that salicylic acid is very acidic as compared to meta hydroxybenzoic acid as well as para hydroxybenzoic acid. So now what we've seen is that the hydrogen which is attached to the carboxylic oxygen here is acidic in nature. So what we find is because of this acidic hydrogen, carboxylic acids undergo acid-base reactions. That is, acids react with strong bases to give us a salt of an acid as well as water molecule. So what we find here is that when in a solution, this acid dissociates to give us a proton. This proton is accepted by a base which is a OH group here, resulting in the formation of water molecule. So what we find here is that the carboxylic acid has converted into a carboxylate group or a carboxylate ion, which picks up a cation from the base, that is sodium, and it results in the formation of a sodium salt of a carboxylic acid. In the next reaction, again I have shown a reaction of carboxylic acid with sodium bicarbonate. This reaction is a very interesting reaction because with the help of this reaction we are able to distinguish carboxylic acids from other organic compounds such as phenols, alcohols, aldehydes, ketones, amines and nitro compounds. Because it is the carboxylic acids which react with sodium bicarbonate and liberate carbon dioxide from sodium bicarbonate. This carbon dioxide, when passed through lime water, it turns lime water milky. So that means if we give you a compound to test in the laboratory and that compound liberates carbon dioxide from sodium bicarbonate and converts lime water milky, that means the organic compound is carboxylic acid. Now we shall be dealing with very important reactions, that is reactions due to the cleavage of COH bond, which are known as nucleophilic acyl substitution reactions. Why are they known as nucleophilic acyl substitution reactions? Is because in these reactions the substituent which is attached to the acyl group is substituted by another nucleophile. Hence these reactions are known as nucleophilic acyl substitution reactions. But before I proceed with nucleophilic acyl substitution reactions, let us compare carboxylic acids with aldehydes and ketones. In my previous lectures, we have discussed in great detail aldehydes and ketones, and we know that the characteristic reactions of aldehydes and ketones are nucleophilic addition reactions, whereas I have just now said that carboxylic acids and its derivatives undergo nucleophilic acyl substitution reactions. Why is this difference in behavior? That is, aldehydes and ketones both have carbonyl group in them, whereas aldehydes and ketones undergo nucleophilic addition reactions and these acids undergo nucleophilic acyl substitution reactions. So if we look into the structure of an aldehyde and a ketone, then what we find is in case of an aldehyde, the carbonyl group is attached to an hydrogen, whereas if we talk of a ketone, then the carbonyl group is attached to two alkyl groups. And we know that these two groups, that is either it may be a H minus or an R minus, these are strong bases. Since they are strong bases, they cannot be substituted, that is, they are not good leaving groups. So please keep in mind that aldehydes and ketones will undergo nucleophilic addition reactions. Whereas when we talk of an alkyl acid halide or a carboxylic acid, then what we find here is that a carbonyl group is attached to a Y group. This Y can be an OH, it can be a X minus, that is a halide, it can be a ester group, it can be an anhydride group. So all these groups are good leaving groups because they are weak bases. So what happens in this case is that when a nucleophile comes and that nucleophile is stronger than this group here, it will displace it and will take its place. So hence what will happen, that is, the nucleophile will substitute a leaving group and we will get substitution reactions, whereas this is not possible in case of aldehydes and ketones. So if we look into the mechanism, so what we find is in both the cases, whether we talk of an aldehyde or an alcohol, the first step is the attack of the nucleophile. So if I talk of the if we talk of a ketone here, so what we find here is that the nucleophile will attack the carbonyl carbon, and this carbonyl carbon is electrophilic in nature since it is attached to a more electronegative oxygen. So it results in the formation of an alco oxide intermediate. This first step is similar in case of acids also and acid derivatives also, that is, a nucleophile will attack the carbonyl carbon because this carbonyl carbon is again electrophilic because the carbon here is attached to an oxygen and to a group Y. This Y is more electronegative than carbon, so this is highly electrophilic in nature and we get a alco oxide intermediate. Now after this is where the reaction mechanism is different. Since we do not have a good leaving group in aldehydes and ketones, they undergo protonation to give us a alcohol. That is an addition compound. Whereas when we talk of an acid, then what we find is that this Y is a good leaving group, and it is assisted by lone pair of electrons on oxygen, and this Y is pushed out, resulting in the formation of a substituted product, which may be acid halide if we are doing the reaction with of an acid with a thionyl chloride. So the next reaction I would like to compare is, that is now what I've talked of, that is if we are comparing a ketone or an aldehyde with an acid, then aldehydes and ketones undergo nucleophilic addition reactions, whereas acids undergo nucleophilic substitution reactions. Now if we compare the reaction of an acid halide, of an alkyl halide with an carboxylic acid, what we find is that both of them undergo substitution reaction, and superficially we'll find that the substitution reaction of acyl acids, carboxylic acids, are similar to alkyl halides. But what we find in case, that is when a nucleophile attacks, it will attack the carbon, the electrophilic carbon, and that bond will be broken, which will be the weakest bond between C and the attached group. And what we find, that is in case of alkyl halides, the weakest bond is between carbon and the halogen. And what happens here now is that this bond is broken and the nucleophile substitutes this X from the backside. This is an SN2 reaction. Whereas when we talk of a nucleophilic acyl substitution reaction, then what we find is that this reaction takes place in two steps. In first step, the nucleophile will break the weakest bond in the molecule, and we know in case of acids, the weakest bond is between carbon and the oxygen, that is the carbonyl group, and the pi electrons, pi bond breaks here. The nucleophile attacks and we get a tetrahedral intermediate. Now from this tetrahedral intermediate, the leaving group departs, resulting in the formation of the product. Hence, nucleophilic acyl substitution reaction takes place in two steps involving a tetrahedral intermediate, in which the first step is the addition step, that is the reaction with the nucleophile, and second step is the elimination step, in which the leaving group departs. So this is where we will stop, and in the next section we shall be taking the mechanism of nucleophilic acyl substitution reactions in detail, as well as discuss few examples of nucleophilic acyl substitution reactions of carboxylic acids. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, we know that you have lots and lots of questions in mind. So if you wish to ask questions live through our session, then do call us through our toll-free number. Here, our toll-free number is 1-800-110-4380. We would be repeating the same number again, but it's time to take break over here. So after a short break, we will be back, and of course, we would be continuing further and would be taking your queries. Thank you for watching us. Hello friends, welcome back to this session. Friends, you know that today we are talking on nucleophilic acyl substitution reactions of carboxylic acids, and for the discussion on the topic, we have with us in our studios Dr. Aprajita Chauhan. Dr. Aprajita Chauhan is a prolific professor, and she is currently teaching as an associate professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Friends, we know that you want to ask questions. If you have queries, then you are free to talk to us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. Now, I would like to welcome our guest, Dr. Aprajita Chauhan, once again. Hello, ma'am. Welcome.
Hello, thank you. I shall be continuing where I left, that is nucleophilic acyl substitution reactions. And as I've told you, they are known as nucleophilic acyl substitution reactions because we are substituting the group which is attached to a acyl carbon. Second thing, that these reactions are also known as addition-elimination reactions because in them first addition takes place to form a tetrahedral intermediate, and then elimination takes place in which a leaving group is eliminated to form a product. In most of these reactions that we'll be studying, what we find is that the carboxylic acids are converted into acid derivatives. So the product of nucleophilic acyl substitution reactions of acids are, that is, we get acid derivatives like acid halides, anhydrides, esters and amides. We get these reactions, we get these products by reaction of acids with different reagents, with specific reagents. That is, acids react with thionyl chloride to give us acid chloride. They will react if we take two molecules of acid and heat them, or if we take an acid and treat it with acid chloride, we will get an acid anhydride. We treat an acid with an alcohol in acidic medium, it will result in formation of an ester. And when we will treat acid with ammonia, first an acid-base reaction will take place, resulting in the formation of ammonium ion, which on heating will give us an amide. So the aim of bringing about these reactions is to convert OH into a better leaving group. That is, we'll convert OH into a COCl in which Cl is a better leaving group, or into an anhydride in which OCOR is a better leaving group, or OH is converted into an ester, that is OR group, or into an amide in which we are substituting OH into a NH2 group. So what we find is that basically we are doing nucleophilic acyl substitution reactions to get important derivatives which are known as acid derivatives. So now if we look into the general mechanism of nucleophilic acyl substitution reaction, then what we find is that in the first step, the nucleophile will attack the carbonyl carbon. Because this carbonyl carbon is highly electrophilic in nature, that is, it is attached to an oxygen on one side by a double bond to another atom, group Z. Now this group Z can be Cl, OCOCr, it can be OH, that is an acidic group, that is carboxylic group, OR, which is an ester, or an NR2 group, which is a secondary amine. So amide. So what we find in this case is, since these two groups are electron withdrawing groups, this carbon is highly electrophilic in nature, and what we get here is a tetrahedral intermediate. Now in second step, what happens is that this group Z, which is a good leaving group, which may be an halide group or an OH group, this is displaced and it is assisted by lone pair of electrons on oxygen, resulting in the substitution product. So since here what is happening here, first is addition is taking place here, and in the second step elimination of Z is taking place, so we call this reaction also as nucleophilic addition-elimination reaction. So now if we have to draw the product of the nucleophilic substitution reaction, so what we have to now first do is, first of all, you will identify the carbon which is sp2 hybridized. So when this carbon is sp2 hybridized, so the group attached to this carbon will be the leaving group, right? So since it is attached, the carbonyl group here is attached to a CH3 group as well as a Cl group. We know CH3 group, if we remove it, it will be removed as CH3 minus, and CH3 minus is a strong base, hence we cannot replace it. So the leaving group here is halide, that is chloride. And now what we have to do is, we have to identify the nucleophile. So when we identify the nucleophile, what we find is that in the first reaction, nucleophile is NH3. Whereas if we look into the second example, the nucleophile is CH3OH, that is, it is methanol. So now in what we have to do is, remember, is that we are going to substitute, or we are going to replace this Cl with ammonia. And now since we are replacing it with ammonia, so it is not easy. So what you have to remember is that since this nucleophile is a neutral nucleophile, so in this case we will have to remove a proton also. So the nucleophile here will be NH2, the H from here will react with Cl and will be eliminated as HCl, which is the byproduct, and the main product is amide. Similarly, when we do the reaction of an acid, carboxylic acid with methanol, what you have to remember is, you are going to identify the group, that is the carbonyl group. The group attached to it, the OH, will be the leaving group, and the nucleophile, that is, in this case I am going to consider like methoxide ion, if is the nucleophile here, it will replace the OH, and what we will get here is an ester. In this case, the ester is methyl benzoate. So now we can, if we talk of converting carboxylic acids into different acid derivatives, the first acid derivative that we can get from carboxylic acids is acid anhydrides. That is, in this case, we will heat acid molecules, that is a carboxylic acid, to 800 degrees Celsius when it loses a water molecule to form an anhydride. So in this case, I have taken acetic acid. It is heated to 800 degrees Celsius and it loses a water molecule to form an acetic anhydride. But in this case, the yield is not very high. So the better way of converting carboxylic acids into acetic anhydrides is when we heat a sodium salt or a carboxylate salt with an acid chloride. So when we do this reaction, what we find is that the carboxylate ion here acts as a nucleophile through lone pair of electrons on oxygen, and it attacks the carbonyl carbon here, which is electrophilic in nature, resulting in the formation of the tetrahedral intermediate. Now we know that the bond between C and Cl is weaker, and this is weak, and this group will be eliminated as Cl minus, assisted by the lone pair of electrons on oxygen, resulting in the formation of anhydride. So this is a good method of preparing anhydrides, because acid chlorides are very reactive towards nucleophilic substitution reactions. What we find is that if we take a dicarboxylic acid, like if we take succinic acid, that is butane 1,4-dioic acid, this on heating loses a water molecule, resulting in the formation of a cyclic anhydride, which is succinic anhydride. Another very important derivative of carboxylic acids is esters. And carboxylic acids can be converted into esters by doing the reaction of sodium salts of carboxylic acids with methyl iodide or with any alkyl iodide. It could be methyl iodide, it could be ethyl iodide, whatever ester we want to prepare. So what we find is that when we do the reaction of for in this case I have taken sodium butanate with methyl iodide, it undergoes SN2 reaction, that is this carboxylate group here acts as a nucleophile and it attacks methyl iodide from backside, resulting in the formation of methyl butanoate in yield of 97%. And methyl iodide, being a primary alkyl halide, undergoes SN1 reaction because it will be attacked from the backside. Whereas now if I look into the other reaction, which is known as the Fischer esterification reaction, then what we find in Fischer esterification reaction is that is in Fischer esterification a carboxylic acid reacts with an alcohol in presence of an acid. The reaction is in equilibrium, therefore the yield of the ester is not very high. So if we want to move the equilibrium towards the right hand side, we will have to use alcohol in excess. So now if I look into the example of this, so what we find here is that if I take mandelic acid and treat this mandelic acid with ethyl alcohol in presence of HCl, what we will get is ethyl mandalate in 86% yield. And in this case, please remember, to move the reaction in the forward direction, we will have to use ethanol in excess, or what the other alternative is that we can remove water from the reaction as the reaction proceeds. Now if we look into the mechanism Fischer's esterification reaction, then what we find is that in this case, as we've seen here, in this carboxylic group, carbon is attached to a carbonyl group by a double bond and it is attached to a OH group. So this carbon is quite electrophilic, but we have to now increase the electrophilicity of the carbonyl carbon. This we do by carrying out the reaction in an acidic medium when the carbonyl oxygen undergoes protonation and this carbonyl carbon is activated towards electrophilic attack, becomes more electrophilic and is activated towards the nucleophilic attack. Now the alcohol molecule acts as a nucleophile through lone pair of electrons on oxygen and makes a bond with this electrophilic carbon, resulting in the tetrahedral intermediate. Now what happens is this tetrahedral intermediate reacts with another molecule of an alcohol, where again an acid-base reaction takes place and alcohol acts as a base through lone pair of electrons on oxygen and removes this proton, resulting into the formation of an ester hydrate. Now in this ester hydrate, what we have to do is we have to remove one of these hydroxyl groups. So what happens is that this hydroxyl group, one of the hydroxyl groups undergoes protonation and is converted into H2O, which is a far superior leaving group as compared to OH. And now this water molecule is eliminated, assisted by the lone pair of electrons on oxygen. Hence what we get here is we get a protonated ester. So in next step what happens is alcohol again acts as a base and abstracts a proton from this, here resulting from the protonated ester, resulting in the formation of a ester molecule. So what we've seen in this reaction is that acid is acting, that is mineral acid in this case, is acting as a catalyst. In the first step, we are using the H plus to increase the electrophilicity of the carbonyl carbon, and in the last step, H plus is eliminated in form of proton. H is eliminated in form of proton. So now if we look further into the isotopic studies of a carboxylic acid with methanol, what we've done in this case is we have taken isotopic oxygen here, that is we've taken O18 here, and when we do the reaction of a carboxylic acid with methanol, what we find is that this O18 ends up in the ester. That means this O18 is coming from alcohol. So what we can now conclude from here is that the cleavage, these are the bonds which will break, that is the COH bond breaks during esterification, and in alcohols the OH bond will break, resulting in the formation of an ester. So if a question is asked that how will you prove that the reaction during the esterification reaction, the cleavage is between the COH bond of an acid and OH bond of an alcohol, what you will do is you will take isotopic alcohol in which we will take isotopic oxygen, that is O18, O labeled methanol, reacted with an acid, and then what we will find is that is we will get O labeled product will be our ester, whereas water will be unlabeled. So this proves that the cleavage is of COH bond in case of an acid and OH bond in case of an alcohol. Next point that is very important that you have to keep in mind, that the esterification reaction that we are carrying out, we cannot carry out the esterification reaction in presence of a base, because when we will do the reaction with a base, what we find here is that this base will act, the OH minus acts as a base, and it will abstract a proton from here, resulting in the formation of an carboxylate ion. Now what we find is that this carboxylate ion has a negative charge on this oxygen, and alcohol is also acting like a nucleophile. It is also basic in nature because of the electrons here on the oxygen. So what we find is that these two negative species, since they are both rich in electrons, do not react and ester is not formed. Hence we cannot carry out the reaction of esters in basic medium. Next what we find is that if we have a dicarboxylic acid, and then what we do is, that is if we do the reaction of this reaction, then that is we have a cyclic molecule in which you have a carboxylic acid as well as OH molecule in it. So this will undergo intramolecular esterification reaction, that is which will be again catalyzed by sulfuric acid, resulting in the formation of lactones, and lactones are cyclic esters. So next very interesting reaction again of esterification is, that is we can bring about esterification using diazomethane. When we do the reaction with diazomethane, we will get the corresponding methyl ester, and this reaction is very good because it gives us high yields. But the drawback of this reaction is that diazomethane has a tendency to explode. So now if we do the reaction of a carboxylic acid with diazomethane, what we find here is that this hydrogen is replaced by a methyl group here, and what we get here is a methyl ester, that is OH is replaced by a methyl group, resulting in formation of a methyl ester. Similarly, if we take an example, what we find is that is when we use cyclobutane carboxylic acid and do the reaction with diazomethane, we will get methyl cyclobutane carboxylate, and the yield is 100% and the nitrogen is evolved. So now when we look into the mechanism of the reaction, what we find is, if we look into the structure of diazomethane, the resonating structure of diazomethane, what we find is that this carbon is basic, has a negative charge, hence it can act as a nucleophile. So what happens is that when we look into the diazomethane here, this carbon acts as a base and it reacts with an acid. It removes a proton from here, resulting in the formation of a carboxylate group and a methyl diazonium salt. In the second step, now this carboxylate ion acts as a nucleophile and attacks the methyl group of methyl diazonium salt, resulting in the formation of methyl alkanoate and nitrogen is evolved. So this is a very good method for preparation of methyl esters. So what you have to remember in this reaction is, that is when you are doing the reaction, we are going to replace the H, this is a simple way of doing it, with a methyl group here, and that will give us the product. Now the next reaction that we talk of is condensation of acids with amines or with ammonia. Now, as I've already said, that carboxylic acids are acidic in nature because of the presence of acidic hydrogen, and we know ammonia and amines are basic in nature. So what happens is that they undergo acid-base reaction first to form an ammonium salt, and then when we heat this ammonium salt, it loses a water molecule to form an amide. So now what we are going to do is, let us look into the reaction. That is, when we talk of the reaction, what we find here is that this undergoes acid-base reaction to form a ammonium salt of the carboxylate anion, and when we heat it, it forms a primary amide. If we were doing this reaction, say with methylamine, then instead of getting a primary amide, we would have got N-methyl amide, N-methyl alkane amide, that is a secondary amide. So what we have to remember is, when we are converting acids into amides, the reaction will require two steps. First is the acid-base reaction of an acid with ammonia to form an ammonium salt, and in second step there will be dehydration at high temperature to form an amide. A very, very important reaction of carboxylic acids is synthesis of acid chlorides. Carboxylic acids can be converted to acid chlorides by doing the reaction with thionyl chloride or oxalyl chloride, because they form gaseous byproducts that do not contaminate the product. Thionyl chloride reacts with carboxylic acids to form acid chloride and SO2, which is emitted out, whereas oxalyl chloride forms HCl, CO and CO2, which are again given out. So now what we look into the reaction, so these reactions are very important because the side products are gaseous and they are eliminated and they do not contaminate the main product, that is the acid chloride. So why is thionyl chloride a good halogenating agent? It is a good halogenating agent because thionyl chloride converts the OH group of the acid into a better leaving group, and because it provides the nucleophile Cl-, which will displace the leaving group. So if I look into the reaction of benzoic acid with thionyl chloride, what we find is that the OH group is replaced with a halogen and benzoic acid is converted into benzoyl chloride. So the mechanism of this reaction is very interesting, or I'll say it is similar to what we've discussed previously. That is thionyl chloride here. Please remember, in thionyl chloride, this sulfur is attached to 3 electron withdrawing groups, that is to oxygen and to halogens. So this sulfur is electrophilic in nature. Since sulfur is electrophilic in nature, the acids act as nucleophile through lone pair of electrons on oxygen, resulting in the formation of a tetrahedral intermediate. Now what we find is in this that the chloride ion is eliminated or expelled from this tetrahedral intermediate. That is, this is assisted by the lone pair of electrons on oxygen, and this chlorine is expelled as of chloride. But in the next step, this chloride now acts as a base and removes this proton from here, resulting in an intermediate which is a chlorosulfite anhydride. So what we find here is that we have converted a OH group into a good leaving group. This is a good leaving group here, that is SOCl. This is a good leaving group. SO2Cl is a good leaving group. Now in the next step, what happens is the liberated chloride ion now acts as a nucleophile and attacks the electrophilic carbon of the mixed anhydride, resulting in the formation of a tetrahedral intermediate. Now this tetrahedral intermediate will eliminate the leaving group, which is SO2Cl, and this SO2Cl will now break into SO2 and Cl minus, which are the side products, and the main product is the alkanoyl halide. So what we find here is that the tetra intermediate expels the leaving group, which splits into sulfur dioxide and chloride ion, and acid chloride is the major product which is formed. Now in my next lecture, I shall be discussing the reactivities of acid derivatives towards nucleophilic substitution reactions. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session on nucleophilic acyl substitution reactions. Friends, you are requested to write to us at info.cec@nic.in. This is the ID where you can post your feedbacks as well as your questions too. We are going to meet again soon and would be discussing more. Till then, take care. Goodbye. Thank you. Thank you once again.